So today we're going to look at density-dependent dynamics, and we're going to start to do that, first of all, by reviewing briefly the basic assumptions of Malthusian growth. There are two fundamental assumptions in Malthusian growth: that all the individuals of the same population have access to the same amount of resources, regardless of population abundance. Okay. Doesn't mean it's a lot or it's a little. They have all the same amount of resources. And also, the second assumption is that population abundance or density do not affect basic ecological processes such mortality and reproduction. Okay, we know that this is not true in a lot of cases. Eventually, this is not true. A population can grow in a Malthusian way for some time, but eventually we'll start to find limitation to that rate of growth because space or resources will be limiting, will not be enough to support an ever-growing population. What are the basic features of interspecific competition? The basic feature is that the shared resources are often limited in limited supply. There might not be enough of the resources for any given individual to survive or to reproduce, as well as when, at the same level when individuals are present. The result of competition, what actually happens, is that birth rate might actually decreases, or the natural mortality rate might increase as a consequence of this competition among individuals of the same population. In ecological terms, this means that population growth rates, can be constant, sometimes will start to decrease, and population size cannot grow indefinitely forever. The effect of any individual increases with increases number of competitors. And the most relevant drivers in these processes is the density of the population in a given habitat, the number of individuals that are present in a given area. And that's the reason why this is called density-dependent dynamic. Okay. In brief, what actually happened, as you can see here, is that in a diagram which represents on the horizontal axis the density of the population, on the vertical axis the fundamental demographic rates, that is the birth rate and the mortality rate. What actually happens is that birth and mortality can now be constant as we assume for Malthusian growth. But eventually, mortality will start to increase with density and birth may start to decrease with density. And so at some point, what actually happened, as you see here in this point, is that birth rate equal mortality rate. So the population becomes stationary because there is a turnover of individuals, but the number of births per unit time average the number of deaths per unit time, and so the population tend to stay constant to this level. And this is a very important point. It's called carrying capacity in theoretical ecology, and we will often refer to it as capital K. Okay. In brief, what actually happened is that whether we see the dynamics in continuous time or in discrete time, the small r, the per capita intrinsic instantaneous growth rate, or small lambda, the finite growth rate of the population, are not constant, okay, but they depend upon density. And we want to express this by saying, rewriting the equation and say that rather than the small r, we have capital R, which is a function of n, or capital lambda, which is a function of the number of individuals in a given generation. And so you can see here in these two diagrams here on the bottom, R is not constant, it decreases, and eventually the per capita intrinsic growth rate becomes negative, and for as far as concerned lambda is the finite growth rate that drops below 1. Okay, so if the population is below the carrying capacity as being indicated here, the per capita intrinsic growth rate is positive, and that means that when the population, the derivative through time, will be positive as well, so the population will tend to increase. Okay, but on the other end, if the population density exceeds the carrying capacity, in this specific case, what actually happened is that R becomes negative, the population will start to decrease. Likewise, for when the use the discrete time approach to describe the population dynamics, if the population density is below k, lambda is larger than 1, the population will tend to increase generation from generation. And if it is above, the carrying capacity will start to increase. So that carrying capacity, some caveat, we'll see that later, is an attractor. The population will tend to go there, and so it might represent, as we will see, an equilibrium point for the population. Just in terms of taxonomy of models and ideas of how density dependent might occur, a classic distinctions you can find in theoretical ecologies is to refer intra-specific competition, so intra because it's between individuals of the same population, and intraspecific between individuals of the same population, and density dependent because depend upon the density of the individual. So a classic distinction is between exploitation competition and interference competition, as you can see here. In the case of interference competition, the competition might occur when individuals really get in touch. They contact each other, they fight to defend the territory, which might happen, for instance, for benthic population or coastal population that uses resources that are finite, really, in terms of amount of space or habitat of refugees, for instance, that are available. Okay. In exploitation competition, what actually happened, there might be intraspecific competition even if the individuals don't even contact each other, or the fact they contact each other is not that relevant. What is relevant is that they are exploiting a common pool, a common reservoir of resources, and basically the presence of other individual reduces the amount of resources that each individual has access to. There are other type of ways of basically slicing, these large aspect of density dependent competition. Here we can see a taxonomy of density dependent models we're going to look at in this specific class. First of all, a classic distinction between continuous time model and discrete time model. There are a few differences that are relevant, and we will see that. The most important things is that in continuous time model, we will see what is considered sort of a pillar in theoretical ecology. You will find in any book of ecology and population ecology, that is the logistic model. And in fishery management, there are other generalized logistic stock recruitment or surplus models that we will briefly see. I just want to stress out, this is logistic model within the context of population biology, and it's something that is very different from the logistic regressions that you might have seen in other contexts. In discrete time model, we will see Beaverton-Holt stock recruitment model, Ricker stock recruitment model, and we're going to look at the graphical solutions by using cobwebbing. It's very useful to visualize the dynamic of this population. And then we're going to talk also about instability and transition to chaos that some of these times models, might exhibit. And last but not least, we're going to spend some time to talk about the inversity density dependent dynamics, and specifically about the Ali effect and the fact that when there are density effects on population dynamics that occurs not only when there is crowding, but there is a lot of individuals that compete for resources, but also when the population density dropped to really low value. This is typical for broodcat spawners, for instance. This has been documented for starfish, has been documented for sea urchin, for our model species, the abalone, for instance. These are broodcat spawner. The male and females release gametes in the water column, and if their density is too low, the fertilization success might drop down quite rapidly. And this effect is called Ali effect. It might also happen for instance, marine mammals that have a very significant social structure that, for instance, use like hunting strategy that exploit, basically the possibility of leveraging on a group of individuals that try basically to earn their resources. In these cases, disrupting the social structure might have very negative effect on the reproductive success and the viability of the population. So we're going to stop here and transition to the next video.